Hello, I'm Hyunseung Hwang from KAIST, and I'm going to present our work XClusters, a framework for explainability-first clustering technique. When we perform clustering algorithms to analyze data, clusters may not be easy to understand, even if they are accurate. For example, explaining demographics of clusters formed from trend data such as credit card transactions, item purchases, and Google search trends is difficult. In the figure below, there are two major clusters that represent spending trends during COVID-19. Simply listing the demographics of individual points in the cluster is lengthy, and pinpointing out the features that distinguish the two clusters is difficult. However, we can use decision trees that can provide a succinct summary of the demographics of the two clusters. Our goal is to find a way to provide as succinct decision trees as possible, while still accurately representing the clustering. Explainability-first clustering tried to reduce the size of the decision trees by fitting the best decision tree given a set of fixed clusters. For example, let there be 5 clusters generated from a clustering algorithm. These clustering algorithms only focus on generating high-quality clusters. From the generated clusters, explainable clustering algorithms find the best decision tree that fits the clusters. Our approach, explainability-first clustering, performs both clustering and decision tree training holistically to find more explainable decision trees while possibly trading off some of the clustering quality. The goal is to balance the clustering quality and decision tree explainability. In our problem, we assume that smaller decision trees are more explainable as it is easier to read. Back to our example, instead of using a fixed set of 5 clusters for decision tree training, explainability-first clustering merges the clusters into a single cluster for better explanations. The clusters have a slightly larger distortion as a result. To formulate our problem, we make 2 extensions to explainable clustering. Since we are performing clustering and decision tree training together, there are now 2 sets of attributes: accuracy features that are used in original clustering and explainability features that are used in decision tree training. The 2 sets may overlap. We also extend the given clustering algorithm. We assume the clustering algorithm can adjust the number of clusters k and uses a distance function for its clustering. We minimally extend the distance function by combining 2 distance functions. Let us define adist as the original distance function using accuracy features. We also introduce edist, which measures distance using explainability features. Intuitively, smaller edist within clusters results in smaller trees as the explainability feature are also similar to each other. So our final distance function is to take a weighted sum of the 2 distances using a ratio called alpha. To holistically optimize cluster quality and explainability, we minimize the cluster distortion d plus the tree size n. The cluster distortion is the sum of square of the distances between examples and clusteroid for cluster quality. The tree size is the number of nodes in the tree. To generate different clusters, we tune 2 parameters: the number of clusters k and the ratio of adist and edist alpha. As iterating through all combinations of k-alpha pair is expensive, we identify and utilize monotonicity properties for efficient optimization. We observe monotonic relationships between k, alpha, n, and d. As we can see in the lower left figure, when k increases, the number of nodes increases to explain more clusters, while cluster distortion decreases as we can distribute data points into multiple clusters. As we can see in the lower right figure, when alpha increases, the clustering algorithm favors clusters with similar explainability features. As a result, the clusters tend to have a smaller number of nodes and higher cluster distortion. The properties are not guaranteed to perfectly hold, but the idea is to exploit monotonicity as much as possible. We now reformulate our problem to monotonic optimization. As changing k and alpha have opposite effects on d and n, we rewrite the objective function to minimize the difference between two monotonic functions. F captures decreasing d and n when alpha and k increase respectively. G captures decreasing d and n when alpha and k decrease respectively. Rewriting the objective functions enable us to use an existing branch reduce and bound algorithm. Here is an overview of the branch reduce and bound algorithm. Given the domain of parameters, as in the lower left figure, we compute the lower bound and upper bound of the objective for each block. We then divide the unexplored blocks into halves and compute the bounds for the new blocks. We discard blocks where the lower bound plus some tolerance value is larger than the smallest upper bound found so far. We terminate the algorithm when there are no blocks left to prune. The lower bound of each block can be computed as follows. Using the monotonicity properties, the lower bound can be found by evaluating clusters and decision trees generated using the top left and lower right parameters in the block. In other words, given a block on the right, we can generate clusters and decision trees using the k1 alpha 2 and k2 alpha 1 pairs. Because we are minimizing the objective value, the upper bound can be computed using any values on the block. For efficiency, we evaluate the upper bound using the same parameters that were used in computing the lower bound. In particular, we take the minimum of the objective function using k1 alpha 2 and k2 alpha 1, where all the d and n values have already been computed to generate the lower bound. The complexity of the overall algorithm is shown in our paper. Let's take a look at an example. Let the tolerance epsilon be 0.1. Given two blocks B2 and B3, we can see that B3 has a smaller lower bound. We thus split B3 into B4 and B5. We compute the upper and lower bounds for the new blocks. However, the lower bound plus epsilon of B4 and B5 are larger than the upper bound of B2. As a result, we discard B4 and B5. As B2 is the best block, we return B2's upper bound as the final result. Through our experiments, we demonstrate two major points. First, we show that XClusters balances accuracy and explainability effectively. Second, we demonstrate how XClusters improves on existing explainable clustering. In our experiments, we compare XClusters with three baseline methods. The two-step baseline first performs clustering and then performs decision tree training. The number of clusters is determined using an elbow method and is fixed from then on. The grid search baseline exhaustively going through all possible k and alpha values. Here we set k to range between 3 and 11 and alpha to range between 0 and 1 with 0.05 increments. Bayesian optimization is a state-of-the-art hyperparameter tuning method that works in a general optimization setting. We use 10 to 30 initial points and iterations. XClusters is our method. In comparison to Bayesian optimization, the key difference is that it performs monotonic optimization based on the monotonicity properties. We use a real-world credit card dataset with 5.7 billion transactions that is worth $120 billion for 2,551 demographics. Other real-world datasets show similar results. Please refer to the paper for the details. We empirically verify the monotonicity assumptions which form the basis of our algorithm. We show that monotonicity property mostly hold for all three datasets. The table below compares XClusters with the other baselines in terms of our objective function, d plus lambda n, and runtime. Recall that when using two-step, the number of clusters is determined during clustering only. Since there is no further adjustment of k, the overall runtime is small. However, the large tree size contributes to a high overall d plus lambda n value. Grid search, Bayesian optimization, and XClusters balances cluster distortion and tree size more effectively than the two-step baseline. The three methods dramatically reduce the tree size in exchange for cluster distortion. However, we can see that XClusters has the smallest runtime as it exploits the monotonicity properties. In the beginning of this talk, I mentioned that XClusters can improve explainable clustering because the reference clusters are no longer fixed and can also be optimized. In this experiment, we show how state-of-the-art explainable clustering method called explainable k-means can be improved when using with XClusters. As a result, XClusters is able to better balance d and n and produce an objective value that is smaller than explainable k-means. Explainable k-means has a high node count n because its fixed reference clusters happen to require a large decision tree to explain. In our work, we propose a new paradigm of explainability-first clustering that holistically optimizes clustering distortion and decision tree size. We identify and utilize the monotonicity properties for efficient optimization. In our experiments, we show that XClusters outperforms explainable clustering by balancing cluster distortion and tree size. Thank you for listening.